X-ray makes you rethink it.
I don't know. Calculator is very typing stupid things.
Yeah, we need it better than me. Calculator on the test.
Yeah, but I'll say it.
But at least in the final, you can try it. It's not like a base house is, you know. Don't say that. No, that's not. That's not. One thing I understand was if you're running this stuff, because it's like so many utilities on it.
No, I had. It was.
Okay, so
I wish I. He's the only one that uses. Hey, you just run your which if I had all that machine like. Yeah. That's all I mean.
so we're gonna finish Laplace transforms and we're gonna use it to. So we've got all this work that we've done trying to compute Laplace transforms or computing inverse Laplace transforms. So we did this one. This one was like trying to come up with what would have given me this after I took the Laplace transform of it. And yeah. There's no word problems. We didn't get to cover any word problems for systems of differential equations. I mean, if we had time, then there were ways to cover word problems that use these systems of differential equations, like using like circuits with loops, multiple loops and stuff. Yeah, so you're spared from, this is the only test that doesn't have word problems. But there'll be word problems on the final because everything we learned in the past will reappear. But we didn't have time to cover word problems. There's just not enough time for me to do everything. Maybe I'm a little too thorough because I move kind of slow. So we took the inverse Laplace transform of this. Now let's look at this one. So like 1 over s minus 5 cubed. Let's go back to this table here. Oh no. If you look at this table here, it kind of looks like, you see here, I had the t raised to the n here, the Laplace transform raised to the n. If you plugged in n is equal to 2 is 2 over s cubed. So this kind of looks like the Laplace transform of t raised to 2, right? T squared. But with what modification to it? The s cubed that would have been in the bottom has now become an s minus 5 cubed. Yeah, exactly. So there's a shift. There looks like there's a shift going on. And so I'll write here, it looks like a shifting. On shift on the s cubed with c equal to 5, because it would have been 5 right here, which means that e to the 5t. So what you're going to do is we're going to say that we know that, so for instance, the inverse Laplace transform of 1 over s cubed is equal to, we actually computed that, this orange thing, ln of inverse ln of not inverse inverse Laplace of 1 over s cubed we found is 1/2 t squared, so we'll just reuse that. But we know that so the inverse Laplace transform of this right here will just be basically the same thing as this, but with a shift going on. So e to the 5t t cubed. Okay. So that's just like, it's squared, sorry. That's like, I see this looks kind of like 1 over s cubed, but all the s's have been replaced by s minus 5, which is like a shifting theorem. So that's the inverse Laplace transform of that. This one isn't even asking for an inverse Laplace transform. This is just saying compute the Laplace transform of this thing and confirm that it's equal to this. And then we'll later use this result in computing other inverse Laplace transforms later. We know that like from before, this is like going back to the previous section, that this is like the Laplace transform of 1 minus b sine of bt, because you could split this into two Laplace transforms because they're just subtracted. This is due to linearity of integrals. And if you look at this one over b, I guess you could pull that out because it's just a constant. The variable is t. And so you'll have this minus this one you'll have to keep. But we know sine of bt, that one is b over s squared plus b squared. You'll be given, so you don't have to worry about it on the test, but on the final, I'm going to give you a page full of these Laplace transforms, so you don't have to use your formula sheet. You don't have to use space on your formula sheet. The t cosine of bt, we did this before, I think. The Laplace transform of t cosine of bt is this right here. T cosine of bt, Laplace transform was this. I'm just going to copy and paste that. And these b's cancel. And we're left with just, I'm going to combine this into one fraction. The common denominator would be this guy, because this guy's the squared one. And then this one has a 1 in the top, but it's missing an s squared plus b squared. And then this will be minus s squared minus b squared, because there's a minus right here. And then you have this s squared, and then once you distribute this minus, and this will cancel. This would be b squared plus b squared, because it's minus and a minus, so you'll get 2b squared over this denominator, which confirms this statement right here. So the Laplace transform, this is equal to this. So if I asked you what is the inverse Laplace transform of this, it would equal this. This goes hand in hand, right? So if the Laplace transform of this is this, then if I said compute the inverse Laplace transform of this orange thing, it's going to be this. And this is a helpful inverse Laplace transform. We'll discover that this actually is helpful for us later. But it would be hard if I just said compute the inverse Laplace transform of this, because it's going to be hard for you to notice that it's actually going to equal this. So this is just doing it this way and then noticing, okay, if this is true, then we know the inverse Laplace transform of the orange has to be purple. So if we look at, we're going to use that right away for this one. So when we're computing the inverse Laplace transform of this, again, you could split this into two fractions. So it's going to be like the 3s over the s squared plus 4 squared. And then there's going to be a minus 5 s squared plus 4 squared. Right? This is just taking the fraction and splitting it into two fractions. Then I can say I can just compute the inverse Laplace transform of the first fraction. Minus the inverse Laplace transform of the second fraction. And if you look at this one, I guess a question I could ask is, I have these two for you right here. And you're just going all of these, you're just going to use the table. But you got to know which one looks relevant. So for this orange one, do you think the top one or the bottom one is relevant? The top one, because the top one has, oops, I'll use orange. The top one has s in it, and there's an s right here. This one has just a b, so it's not going to be right. So not only do we think we are using the top one, which is correct, but what would the b be? Would it be, it'd have to be 2 because the bottom has to be a 4 here. So you have like b squared has to become a 4. And you have to use the bottom one because this top one, you can always compensate by multiplying by some multiplicative factor. But there's no way if you chose like b is equal to 3, this will be a 9 down here, and there's no way to compensate and fix that later. So b will have to be 2. Now, if you used b is equal to 2, then it will be 2 times 2, which is 4s over the s squared plus 4 squared. But what we have here is 3s squared plus 4. So you have to, yeah, exactly. So you're going to say the inverse Laplace transform of, I'm going to compensate for that by multiplying by 3 to force the top to have 3, and then divide by 4 so that the 4 goes away. And we know this guy, the inverse Laplace transform of this, we know from this table right away, but we're trying to make sure we rewrite this in some multiplicative factor times a Laplace transform we know. This 4's will cancel into the 3 will be there, and then we have that. And then let's do the other one, inverse Laplace transform of this right here. So of course, now you're probably like, I'm going to look at the second one for this one. This one doesn't have an s on the top, it just has a 5. But even though there's a 5 on the top, what does the b have to be? Yeah. Again, it has to be 2 because you need this 4 on the bottom. So if you use the b as 2, then it'd be 2 squared times 2, which is 8, over the thing we want on the bottom is s to the 4th, this. So we'll have this 8s squared plus 4 squared. We need a 5 here, so we'll be multiplying by 5 over 8. And then you'll have this piece that we know. Sorry. And that's it. So we have expressions that we've rewritten. They're the same thing though, 8's cancel 5. But now, I mean, one thing you could also do is you could pull these constants out. And if you do that, then you just have, of course, 3 over 4 times the inverse Laplace transform of this thing minus the 5 over 8 inverse Laplace transform of this thing. And then we know right away what the inverse Laplace transform of these are. So this one is a 4s squared. We just said that that's exactly this thing with the b being 2. So that means that it'd be t sine of 2t. T sine of 2t. And then we're going to have minus 5 over 8. We're going to take the inverse Laplace transform of this, which we said is basically this entry with b equal to 2. So that means that you'll just have all this in parentheses, 1 over 2 sine of 2t minus t cosine of 2t. And this second entry is this up here, is this result that we had just done a moment ago. So it's a useful inverse Laplace transform that we needed to use to get this inverse Laplace transform. Okay, so we're good with that. All right, so then we're almost done with computing inverse Laplace transforms. There are certain types of inverse Laplace transforms that we'll have to do partial fractions to be able to solve. They're not that bad. So for example, this 1 over s squared minus 9, you could look at the table, but there isn't any entry on the table that actually will give you useful, yeah, there's nothing on the table that's useful for being able to compute the inverse Laplace transform of this. So what we're going to do is we're going to decompose this into its partial fraction expansion. So we're going to say this, of course, the bottom factor is as s plus 3 and s minus 3. So you'll have a over s minus 3 plus b over s plus 3. And you can do partial fractions. You'll just say 1 is equal to a s plus 3 plus b s minus 3. And of course, if you plugged in s is equal to 3, you can eliminate the b. If you eliminate the b, you just get a is equal to 3 plus 3 is 6, 9. So a is equal to 1 over 6. If you plugged in s is equal to -3, you can eliminate the a. You'll just get 1 equals -6b, which means that b is equal to -1 over 6. So then you'll have your partial fractions are 1/6 times 1 over s minus 3 minus 1/6 1 over s plus 3. And that means that this here decomposed into these partial fractions. Oops. Right, this is the same. I just said that I just took the thing and just rewrote it as a partial fraction decomposition. But of course, now I can just take the inverse Laplace transform. So the inverse Laplace transform of this 1 over s squared minus 9, which there's nothing on the table that can help us with, if you rewrote it out, becomes this. So it's the same as taking 1/6 the inverse Laplace transform of 1 over s minus 3 minus 1/6 the inverse Laplace transform of 1 over s plus 3. And these you know from the entry from the table very easily. So 1 over s minus 3 is actually e to the 3t. This is minus 1/6. This is just going to be e to the -3t. These inverse Laplace transforms are just the exponential ones that are easy. So what we've done is took something we don't have anything on the table directly for, decomposed it into partial fractions, and each term in that partial fraction expansion are easy Laplace transforms. So we can just do those. So that's basically the only thing that this section is doing, is they're just saying, I don't have anything on the table that gives me the inverse Laplace transform of s plus 1, s squared plus s minus 2. Well, what I could do is I could do the t partial fractions of it. It's going to generate a bunch of terms that are separate fractions due to the partial fraction decomposition. And each of those terms are simple Laplace inverse, that we can find an inverse Laplace transform. So you can actually take the factor at the bottom. This decomposes into a s plus 2 plus b s minus 1. And so I'll write out the partial fractions to how to compute a and b. That's just calculus 2. So just so that we get the punchline, you'll get a is equal to 1/3 and b is equal to 2/3 on this. So I'm not going to go through the algebra of showing that a and b are these. But once you have those, then the inverse Laplace transform of this thing that you want is just going to be equal to the 1/3 times the inverse Laplace transform of 1 over s plus 2 plus the 2/3 times the inverse Laplace transform of 1 over s minus 1. And those are also really easy because it's going to just be e to the -2t plus 2/3 e to the t. Okay. So not really that different from before. This is still just a bunch of partial fractions. So this actually is a cubic on the, well, it's a cubic on the bottom, but it's not hard to factor. I'll just write it out. So it's going to be, of course, s comes out. So there's like clearly s that's common across all of these. And then the other two the remaining actually factors to this. So you now have 3 entries in your partial fractions. You have a over s. You have plus b over s minus 2. And then you have plus c over s minus 1. It's really not that different. Again, you can compute the a's, b's, and c's using what you remember from Calc 2. I'll post all the work here just for thoroughness later, but the point is that you'll just get these. So then when you're trying to compute the inverse Laplace transform of this, you're just going to say the inverse Laplace transform of this fraction right here, since it decomposes into those pieces, would be like 1/2 times the inverse Laplace transform of 1 over s. I'm already just pulling the constants out. So this a, b, and c are these entries, but I'm just leaving those out and just saying this is going to be 1/2 inverse Laplace transform of 1 over s minus 2 plus or minus, because c is equal to -1, inverse Laplace transform of 1 over s minus 1. And the inverse Laplace transform of 1 over s is just 1. So that's just going to be 1/2 times 1. This is going to be 1/2 times e to the 2t. And this is going to be minus e to the positive t. And that's it. Just partial fractions, and then just doing the inverse for each of those terms. Just because this is not an entry in the table. So, but this actually can be decomposed into a bunch of little pieces, and those little pieces are very easy. Inverse Laplace transforms. This one's a little bit tricky. If you were to try to compute the so if you were to try and factor this, you won't be able to factor it. It's going to be complex. The reason it's complex is because if you were to look at this as a quadratic and compute the discriminant, it's b squared minus 4ac. Discriminant is what's inside the square root when you're doing the quadratic formula. Of course, I'm just looking at the bottom. So bottom is going to, the b is 2 squared minus 4 times 1 times 26. And that is equal to 4 minus 4 times 26, which clearly is going to be negative. So you'll have complex. So the way you do this is you just say, I'm going to take the bottom minus 2s is 26. And you could rewrite the bottom as I take the middle entry, which is minus 2, and divide it by 2. So I'll just say s minus 1 squared. Okay, so if you have this, you'll have s squared. And then if you FOIL this, you would have the minus 2s, because there's going to be like s minus 1, s minus 1, s squared, 1 minus s, 1 minus negative s, that's going to be negative 2s. And then you'll have a plus 1, but you need to have a 26. So you need to make up for that by adding 25. This is called completing the square. So we just completed the square in the bottom. And then this, I'm giving you these entries here. This is an S on the top, by the way. But there's an issue here because this doesn't quite fit. It looks like you might be able to use the cosine because there was an S on the top. But the issue is that this bottom is not, this is S minus 1. So if they're both S minus 1, then it'll be like the cosine, but with a shift. But one of them is S minus 1, the other one's S. So it's not quite a shift. So the way that people do this is they say, I'm going to make one of them be like this cosine with a shift. So I'll write S minus 1 on the top because then it'll really be this with a shift. Because the shift requires all my S's to be S minus 1. But I can't just leave it like this because this is like, there's not going to be an A that will ever make this equal this. So I need another entry here. And the other entry is I'm going to look at this sign. And this sign looks like this could be the shift of a sine function, so long as this B is 5. Because this is like a 25, this B could be 5. This S will be kind of s minus 1, but this, so I'll write it here. This right here would be a shift of a sine function because there's only one s for the sine function. So this is like a shift for the cosine. This is like a shift for the sine. But now that I said this is equal to this, I put a and b here because you might have to find what a and b must be in order for this equality to hold true. So I decompose this into something like a shift of a cosine and a shift of a sine, but I can't just leave it like this without finding, I need to find this a and b so that this equality still holds. So let's say, suppose we find what those a and b's are, then the inverse Laplace transform of this, because all I did is I took this and rewrote it out into these pieces. The inverse Laplace transform this would be really easy because it would just be a times what's the inverse Laplace transform, s minus 1 over s minus 1 squared plus 25. It's like this cosine with b equal to 5, but it's been shifted, so it'll be e raised to the something times cosine 5t. The shift was, the c was 1, so it'd be e to the t. This one was plus b. This is like, now that we did this one, what's the inverse Laplace of 5s minus 1 squared plus 25? It looks like, yes, to the, it's the same shift, right? Because it's e to the t, but then now this is a sine of 5t. And we'd be done, right? That would be the answer. The only thing I didn't do is I didn't figure out what the a and b was. So what I need to do is I need to, let's say I was trying to force this equation to be true, right? This s of this over this had to equal this. That means that I can multiply everything by this denominator, and that means that you'll have to have s equal to a times s minus 1 plus b 5b. And you could always plug in s is equal to 1. That'll eliminate this a. So that means b is going to have to equal 1 over 5. Because if you did s, 1 over s. Wait, did I do this right? S is equal to 1. Yeah, it'll be 1 over 5 because s is going to equal 5. 1, right? S will equal 1, and then you're just going to divide by 5. And then for the a, I would do this. I would just multiply everything out and just say s is equal to as minus a plus 5b. Yeah, a is just 1 because you need to match, right? This s and this s has to match. So a is going to equal 1. And it works out nicely because when b is equal to 1 over 5, 5 times 1 over 5 is 1. And then a is 1, so then it'd be negative 1, 1. So this is the other. So in order for this equality to hold, this has to be the a's and the b's. So your answer is going to be this again with this equal to 1 and this equal to 1 over 5. So then therefore your inverse Laplace transform of this guy, which you couldn't do partial fractions into real, into a nice fractions because they're complex roots. But you could complete the square is probably the hardest part about this one. Whenever you have something that you can't write as a factor here with real roots, then you can complete the square. The complete the square actually is nice because you have a perfect square. And these fractions here are perfect squares because s squared and b squared, s squared and b squared. Right? So you're trying to force this to look like one of these denominators here. But then this, it looks like a cosine, but not quite shift. It looks like a cosine that could be shifted, but it's not quite because this is an s on the top. So you got to make, we forced one of them to be s minus 1, the other one to look like sine that's shifted. But the hope is that if we do decompose it like this, then there are A's and B's that will make this equality true. Then it's great because we know the inverse Laplace transform of these fractions. And so it's just going to be b to the t cosine 5t plus 1 over 5 e to the t sine 5t. And that's it for that. I think there's only one more. There's only one more. What is this? Okay, so maybe there's just a couple more. And then we're going to use these to solve differential equation. So this one is a cubic on the bottom. The cubic on the bottom is, so it's hard to factor this in general. So I'll probably have it factored for you, but you could always check that s equals 1 is a root. So you can see, you can check that s equals 1 is a root. And then you do long division and all this. So that's not really important. So in the end, this s cubed minus s squared plus 4s minus 4, it factors to s minus 1, because s equals 1 is a root, and the rest is going to, you have to do like polynomial division, and you'll get s squared plus 4 that's left. And this s squared plus 4, you can't factor any further. So this one right here, you can write a partial fractions for. It's going to be s minus 1. Plus this one, you can't factor any further, so it's going to be s squared plus 4. But does anybody remember what has to be on top of here for the partial fractions when this is s squared? It's not just b or 2b. Yes, exactly, because this is irreducible. And so you have to be 1 degree less on the top. That's how the partial fractions work. And then you just, okay, for this one, I'll go through the trouble of computing the coefficients. So if you multiply this denominator on the top and the bottom, it'd be s squared plus 4 here, plus the bs plus c multiplied by s minus 1. And you can always plug in some particular values. So you can say like s is equal to 1. If you do that, then you can eliminate all of this. This will equal 1 is equal to 5a. So a is equal to 1 over 5. If you plugged in s is equal to 0, I guess you could plug in s equal to 0. If you plug in s is equal to 0, then this will be 0 on this side. You'll have the 4a, because it would be like s squared is 0 squared, and then 4 times a. This b will go away, and that was the point, was that the b would get eliminated, and you'll have c, s minus 0 minus 1, so minus c. So therefore, your c would equal 4a, which we just found is 1/5, so it's going to be 4 over 5. So we got the c and the a. For the b, a common thing to do is you just look at the leading coefficient. So if you multiply this a with this s squared, and then this bs with this s, those are your s squared coefficients. So you'll have as squared plus bs squared, which of course is just a plus b s squared. But if you look at the left-hand side, there are no s squared terms. So that means that this means that this a plus b has to equal 0. Which means that b has to equal negative a, which means that it's negative 1 over 5. I don't know if you have seen this part. You should have seen partial fractions like this, So if you had like an s irreducible, you go one lower. So to find all these coefficients, that's how you would do it. And then once you have those, then you're good, because you just have to compute so that means that I can decompose this into these pieces. So it's going to be like the a is 1 over 5 times 1 over s minus 1. I'm going to split this into 2 fractions. So it's going to be like negative 1/5 s over s squared plus 4. And then this c is going to be 4/5 times 1/s² plus 4. Okay, so you have all these little pieces now. And then we just take the inverse Laplace transform. I think this is the same because I have 2 pages of this just because I thought I'd need more space. So we can just compute the inverse Laplace transform. So basically, I'm just going to say the inverse Laplace transform is going to be of all of these. After you've broken it up into its partial fractions, it's going to be 1/5 e to the t, because this is 1/s minus 1. This one is negative 1/5. This looks like a cosine or a sine. Do you remember now? Cosine 2t because of the 4. And this is 4/5. And this looks like, this one you have to compensate for it a little bit because this looks like the sine, but sine with a b equal to 2, which means there would have been a 2 up here. So you'd have to take this and divide by 2. So it's 2/5 sine of 2t. And that's it. And then, yeah, this is the last one. And then this one, it's already factored. So you're just going to say this is the same as a over s plus 1. But this is a multiplicity of 2. So you need another one with s minus 1 squared. Do you guys remember that? Like when you have like s plus 1 squared, the decomposition is one of them is a over s plus 1, and the other one is going to be b over s plus 1 squared. And this one you don't, even though this is quadratic on the bottom, it's not written as a linear on the top. It's just a b. And then the last one is the classic c, s2. And if you plugged in s is equal to 2, then you'll get, I'll just abridge it and say you'll get c is equal to 1. If you plugged in s is equal to -1, you'll get b is equal to -2. But this whole getting the a, I'm gonna, so what I'm doing is I'm just saying, if you were to multiply everything by this denominator, this a will have to have s minus 2 as well as an s plus 1. This one will be b times s minus 2, and this will be c times s plus 1 squared. And so these will give you these because these are designed to and purposely eliminate. So if you plugged in s is equal to 2, you'll get this entry and this entry to go away. If you plugged in -1, you'll get this entry and this entry to go away, and you get your b. But you still have to find what a is. And I'm going to do the same thing I did before. I'm going to say, if I were to multiply out and just care about the s squared terms, this one doesn't have an s squared term. But this c and this s do have an s squared term. So then if you multiply all the s squared terms, you would have a s squared plus cs squared. But you need this to equal 0 because there's no s squared term here. So that means a plus c must equal 0. So that means that c must equal, a must equal -1. And then you're done because each of these are nice entries on the Laplace transform. So we'll just take the inverse Laplace transform of all of these little pieces now. So it's going to be like inverse Laplace transform of -1 over s plus 1, and then -2 over s plus 1 squared. And then the c is +1 over s minus 2. And this one's going to be -e to the t, -t, minus, so this one, it looks like s plus 1 squared. This looks like a shift that's being done to, so like if you look at the entry for the Tn. Let's just screenshot this right here. Actually, well, no, we'll just screenshot this one. I'll just grab this. So we have this entry on the table. This looks like a s squared, so that means that n must equal 1. So n must have equaled 1. If you made n equal to 1, you have 1 factorial, which is just 1, over s squared. So this looks like this, but shifted. So it's going to be t squared e to the negative t. And there's a 2 in the front. And then you have plus e to the 2t. Because this is just the inverse Laplace. So that's that. Okay. So there's that's just all of these are partial fractions. I just want to cover this one because if you have a multiplicity of 2, then you have 1 and then you have another one. And then the irreducible one. And then the other ones before that, except for this completeness square, are kind of more standard. And then there's a bunch of other ones that the book has, like repeated imaginary roots, repeated complex roots, but we're not going to cover those. We'll just skip those. So this is the final punchline. And what we're going to do is we're going to compute, we're going to use Laplace transforms to solve differential equations. There are a couple more Laplace transforms we need to actually be able to compute. We need to be able to compute the Laplace transform of a derivative and a second derivative. So if I were to ask you to compute the Laplace transform of f prime of t, then I'm just going to use the definition of the Laplace transform. And the definition of the Laplace transform just says, if I want to compute the Laplace transform of f prime of t, all I'm doing is I'm going to take the integral from 0 to pi of e to the negative st, but I'm not plugging in f of t, I'm plugging f prime of t, so this will be f prime of t dt. And so I'll just make it clear that that's actually the new function we're plugging in instead of the derivative, instead of f of t, it's f prime of t. We can do partial fractions on this, so I'll differentiate, I'll integrate the f prime, and then I'll have negative st f of t. And then I'll just say this has to be evaluated from t goes to 0 to infinity. And then you have minus, then I take the derivative of e to negative st, so it's going to be plus after you do that, because there's going to be a negative that pops out, negative s that pops out. And this s I'm going to pull out because this s is actually not the integration variable. So it's going to be 0 to infinity of e to the negative st f of t dt. Okay, so this is the Laplace transform of this, but it looks kind of weird, and we want to probably be careful about this improper integral. So I'm going to look at the inside of this integrand, and also like it is like about 1250. If you need to go, you're fine. I'm going to probably have to go like about 20 minutes, no longer, to try to finish this section on applying Laplace transforms to solve differential equation. But this is all being recorded, so I'll post it. But if you need to go, you're fine. You can go. But if you can stay, then you're welcome to stay and watch me go over this. Yes. No word problems, but there will be eigenvalues and eigenvectors, but just real eigenvalues. Yeah. Thank you. I'll see you. Okay. So this one right here, if I wanted to compute, make sure that this integral exists, because it's an improper integral. So it's like being integrated all the way up to infinity. You probably remember from Calc 2, to converge, we need that this integrand is f of t over e to the st. I'm just moving the e to the st to the bottom. and making it e to the negative st to the bottom, making it e to the positive st. To make this converge, we for sure need this integrand, because it's being integrated all the way off to infinity, we for sure need this to go to 0. This is like your nth term test. Remember, like when you did like series and stuff, like you need it to make sure that if you're summing a bunch of terms, basically, those terms themselves need to go to 0. This is like a necessary, but maybe not sufficient condition, but you know for sure that this integrand, which is this right here, has to go to 0 as t goes to infinity. So this is something that the book says. The book says that that means that your f of t can't be anything. Your f of t has to be so-called of exponential order, which means that this actually will go to 0 as t goes to infinity. So that's something that we'll have to make sure our function f does. Now let's look at this other one right here. This one is, if you actually wrote it out, is going to equal, I'm going to, take the limit as t goes to infinity of, I'm going to say my f of t here, divided by e to the st. And then it's going to be minus by f of 0 over e to the 0. Okay, this is what this means. It just means I plug in infinity into this minus the 0 into this. And I guess plugging in infinity is like, thinking about it as a limit. So I know that I have to have this. But in order for this orange thing to converge, we said that f of t over e to the st has to go to 0 as t goes to infinity. So we know from that that this also better go to 0. Right? In order for this integral to exist, we need to have this be true, which means that this better go to 0. So then at the end, we are left with this is going to be going to 0. So that's gone. You have negative f of 0 over e of 0, but e of 0 is 1, so be negative f of 0. Plus, there's an s in the front here. And what is this? This integral from 0 to infinity, e to negative st f of t dt, that is just the same as the Laplace transform of, so I can write this, right? So this is the same as the Laplace transform of f of t. But is the definition of the Laplace transform of f of t, right? Because this has got f of t in here, e to the negative st. And people like to write that as f naught plus s capital F of s. And this confirms that the Laplace transform of your derivative is just, the order is written, so s f of s minus f naught is the same. These are the same. Provided that the function has this property where it actually goes to 0 as t goes to infinity. This ratio goes to 0 as t goes to infinity, which the book says that the f of t has to be of exponential order, which means that it has this property. Otherwise, you won't have this integral converge, or this term right here converge. So provided that this is true, so the Laplace transform of f prime of t doesn't exist for all functions. It only exists for functions that have this property. But if your function does have that property, then it's equal to this. Now, for the second derivative, we're just going to reuse the first derivative. So the conclusion we got from just doing this right here is that the Laplace transform of f prime of t is equal to, I'll just write it like s Laplace transform of f of t minus f of 0. Okay. So if I were to compute the Laplace transform of f double prime of t, then it's like saying compute the Laplace transform of like f prime of t, but that all being primed. Kind of weird, but I just said like this is like f double prime is the same as f prime of t, but that whole thing taking the derivative of, which is like every single time I see f of t here, I'm gonna write a prime. And this will be minus f prime 0. And the Laplace transform of f prime of t, we just said this is itself this. So we'll have s times s Laplace transform of f of t minus f of 0 minus f prime of 0. And then I'm just going to write this as s squared capital F of s minus s f of 0 minus f prime of 0. The capital F of s is the same as, so I'll just make sure that you remember this right here is the same as capital F of s. And then this should be the same thing we have right here. So all I did was I reused. So this is like saying the Laplace transform of the f prime is this. So f double prime would have been like the same as just putting a prime in all of these f's right here. So that's all we need. Now we can actually use the Laplace transform to solve a differential equation. So like for this one right here, the equation is got y because the book likes to switch to y for some reason. We're used to seeing x double prime and x prime and y, but the book somehow when it goes into Laplace transform decides to switch and use y's instead. You could use, this is constant coefficient though, because there's a 1 in front of this, a -6 in front of this, 5 in front of this, and this is a constant input. So this right here, you can just use method of undetermined coefficients. It's not really that interesting to watch me do the method of undetermined coefficients, so I'll post the method of undetermined coefficients right here. But the idea is, can we solve the same equation using Laplace transforms? So how you do that is like this. So what you're going to do is you're just going to take this and take the Laplace transform of the whole equation. So we'll take the Laplace transform of the whole equation, not the inverse, just the Laplace. Take the Laplace transform. I've copied this right here, the ones that we just computed earlier, which is the Laplace transform of these derivatives. So the Laplace transform of y double prime is going to be s squared, and I'm going to use capital Y of s minus s little y at 0 minus y prime at 0 minus 6 times the Laplace transform of y prime is s capital Y s minus little y 0 plus 5 times the Laplace transform of y is just capital Y. And then the Laplace transform of 2 is 2 over s, because remember the Laplace transform of 1 is 1 over s. So this converts everything into, we converted the equation. We took the Laplace transform of the entire equation, every term of the equation. That's why we needed to find the Laplace transform of the derivative and the second derivative, because that's how we can convert y double prime and y prime. They give you these initial conditions. Because y naught is equal to 0, that means this goes to 0. This is -1 because y prime is -1. And then, of course, y naught is equal to 0, so this goes away. And then it simplifies to s squared, capital Y of s. This is 0. This is going to be negative of -1, so +1. And then this is going to be minus 6s y of s. And then there's going to be a 5 capital Ys is equal to 2 over 5. 2 over s, this is s. And then I'm just solving now. I'm going to just solve for capital Y of s. It's just an algebra problem now. I'm just solving for capital Y of s. So I'm going to consolidate all my y of s on the left. And I'll notice that there's an s squared. There's a minus 6x s and a plus 5. which are all attached to the ys. This one is the only thing that doesn't have a ys, so I'll move that to the other side. And so you'll just have 2 over s minus 1. And then you can, I guess if you wanted to, you could just multiply everything by s if you want to get rid of this fraction here. So it'll be like s times s squared minus 6s plus 5 times ys. This will be 2 now because you multiplied by s. This will be 2 minus s. And then you can divide everything. So your ys is going to equal 2 minus s over s times s squared minus 6s plus 5. Okay, so what do we do? We took the equation, we took the Laplace transform of the entire equation. Whenever we see y double prime and y prime, we have to use the results we just did, which is computing the Laplace transform of the derivative and second derivative. The initial conditions can get applied immediately, right away. So like anytime you see little y 0, little y prime 0, those are going to be equal to whatever they tell you here. And then you, of course, took the Laplace transform of 2, which is 2 over s. The Laplace transform of y is just capital Y of s. And then you're just solving using algebra for the capital Y of s. But capital Y of s isn't our solution, because our solution is little y of t. But what can we do to this to get little y of t? Any ideas? This is capital Y of s. Capital Y of s is like the Laplace transform of our solution. So I'll write that down up here. Capital Y of s. What is capital Y of s? Capital Y of s is the Laplace transform of our solution y of t. So we just have to do the inverse Laplace transform. So what's going on is we're taking our problem and transforming it using Laplace transform. Now that has the effect of taking a differential equation and making it into an algebraic equation. We solve for the capital Y of s, but that is the Laplace transform of our solution. So we just have to invert this back. So we're just going to take the inverse Laplace transform of this thing right here. And this requires us to, so I'll just make a note here that the bottom does factor even more. It's going to be 2 minus s over s times this right here factors to s minus 1 and s minus 5. Which screams like I could do partial fractions on this. So I'll just take this and then do partial fractions. So we'll say one of them is going to be a over s. The other one's going to be b over s minus 1. The other one's going to be c over s minus 5. And you can find these are not that bad. You can find, and I'll write out the algebra, but you can find all of the coefficients. It's going to be a is 2 over 5, b is negative 1 over 4, and c is negative 3 over 20. So then with that, your solution, y of t, would end up being like as if you took the inverse Laplace transform of 2 over 5 times 1 over s, minus 1 over 4 times 1 over s minus 1, minus 3 over 20 times 1 over s minus 5. And each of these are really easy. So you just say this is just 2 over 5. The Laplace transform of 1 over s is just 1. So it's just going to be 2 over 5 minus 1/4 e to the t minus 3 over 20 e to the 5t. And that's the answer. So this is the basic process. Now, if you could do the method of undetermined coefficients, I think that's probably easier. I mean, it's easier for sure for you guys because you're more familiar with it. So you can always check, right, whether you get the same. So I can screenshot something that I have for the method of undetermined. So you can see how much easier it is if you use the method of undetermined coefficients, maybe for this one. So I'll just paste it in here, right here, just right now, so that we see it. So this is like the work here. So this one, you say characteristic equation, right? This is just constant coefficient. So R is equal to 1 and 5. That means it's like your homogeneous solution is C1 e to t, C2 e to the 5t. But this is just a constant input. So that means your particular solution would just be A. You plug it in, you get 2 over 5. And then you apply your initial conditions. You get C1 is equal to negative 1/4. C2 is equal to negative 3 over 20. And then you write this out, right? That looks a lot easier than, I guess, doing the Laplace transform, although you'll get the same thing. So I can copy this solution we got using Laplace transforms and paste it up here, and you can see that they're the same, right? 2 over 5 minus 4 1/4 e to t, negative 320 over times e to the 5t. So they are the same. But the process is you take the equation, you transform it, and then you do algebra to find what capital Y of S is, but that's not our solution. That's the Laplace transform of our solution. With something, transform the course back to its solution. And that's like kind of something I found. It's a very common technique in differential equations. Laplace transform is one of many transforms that exist. You may have heard of Fourier transforms. There are Henkel transforms. There's like all kinds of different transforms. And, those get used to transform differential equations, either ordinary or partial differential equations, to an algebraic equation. And then you can solve an algebra problem and then invert it back. And for the one that we just did, it's mostly to illustrate the process, although it looks a lot harder to do when you could have done the method of undetermined coefficients. But the point is that you would get the same thing if you did use a Laplace transform. So when is Laplace transform useful? It may be useful when you have something more complicated, like you have, for instance, e to the negative 3t times sine of 4t. Again, this you could use method of undetermined coefficients, because the right-hand side is of a form where you can apply a method of undetermined coefficients. And I went ahead and did the method of undetermined coefficients, but there's actually a lot of work, and I use computer software to compute these derivatives. The reason is because this right here, when you compute the homogeneous solution, it conflicts with the particular solution. There's terms that match. I have to multiply by t. So you have your particular solution form is t e to the negative 3t times a cosine of 4t plus b sine of 4t. That has to do, you have to do product, like a triple three-way product rule. And then you have to do the product rule on that, or you have to do the derivative of that. And then it blows up, but if you simplify it, it becomes this. And then you plug it in and you match, all these terms. And it's like a ton of work to do the method of undetermined coefficient. So the Laplace transform would be easier for this, which I will post right here. I could do it, but I want to be mindful of you guys because I feel like this one's even more interesting. So I'll do this one, and this will be like the last thing. So if let's say you have an equation like this, and you have a fifth degree polynomial times e of t, what you'll do is you'll first find the homogeneous solution. I designed this so that it'll be a double root. So you'll have c1 e to the t plus c2 t e to the t. It will conflict twice with your, so your particular solution, when you have a polynomial times an exponential, would be a general fifth order polynomial, a0, a1t, a2t squared, a3t cubed, a4t to the fourth, a5t to the 5, times this exponential. But the fact that it matches two of the homogeneous terms, I'd have to multiply by t twice. So your particular solution will be t squared times all of this times e of t. Now, if you were to do the method of undetermined coefficients, you'll have to take the derivative of this, and then you'll have to take the second derivative of it. I actually used Wolfram Alpha. It can compute it for you, actually. It will compute the first derivative of this thing, there's a bunch of product rules, and then you'll get this. And then you can actually ask it to compute the second derivative, and it'll give you this giant thing. And then you'll have to plug this in and then match coefficient, match terms on each side. There are how many coefficients? There are there's 6 undetermined coefficients, right? A0, A1, A2, all the way up to A5. So there'll be like at least 6 equations when you try to match each side. And you'd be doing like this for hours, and you'll probably make a mistake in the meantime. So we're going to use the Laplace transforms to solve this instead. And it turns out to be quite easy when you use Laplace transforms for this. So the idea is that I'm going to take our equation and Laplace transform it. So we're just going to say, like we just did before, we're going to take this and we're just going to Laplace transform the equation. Okay, so let's do that. So y double prime is going to be s squared. I'm just going to use this result we had right here. S squared, capital Y of S, minus S, Y, little y of 0, minus little y prime of 0, minus 2 times the Laplace transform of y prime is going to be S, capital Y of S, minus little y of 0. And then the Laplace transform of y is just capital Y of S. Okay. And then I'm going to just take the Laplace transform of all of these. So if you were to distribute the E of t on each of these, they are like a shifting theorem applied to t to the 5th, t to the 4th, t to the 3rd, and all so forth. So you'll have to remember, we'll just have to go back and remember what's the thing for, I must have had a screenshot for this somewhere, for t squared, t to the n. So we'll just grab this again. I'm going to leave it up here. Okay. So we have t to the n. This is t to the 5. So it's going to be 5 factorial over, normally it would be s 5 plus 1, so it'd be s to the 6. But because it's being multiplied by e to the t, it's going to be what instead? Using the shifting theorem. The c would have been equal to
5.
by the c, which is 1 in this case. The same idea for all of these. So it'd be 4 factorial over s minus 1 to the 5th. And then it'll be 3 factorial s minus 1 to the 4th plus 2 factorial s minus 1 to the 3rd plus 1 factorial s minus 1 squared. And I wish I had a little bit more space so that I can fit all this in one line. And then the last entry is the 1. And the 1 is going to be, you could think of it as n raised to 0, t raised to 0. So that, this would just be 0. I guess 0 factorial over s minus 1 to the 1, which I don't have to write. So that's the Laplace transform of this entire equation. We successfully took the entire equation, took the Laplace transform. And then we know these things. So for example, this t naught is, or this y naught, y of 0 is 2. So that means this is equal to 2. Y prime of 0 is equal to 1. Y of 0 is equal to 2. Is that it? That's all. So we have that this is s squared, capital Y. I'm just going to remove the s of s part because it's not really relevant. So it's going to be minus 2s minus 1. And then we have minus 2 times S capital Y minus 2 plus capital Y is equal to all of this. Now I'm gonna just solve, we're just solving for capital Y. So I'm just going to take everything that I see that has Y on this side. So it's going to be S squared is going to be minus 2S and then a plus 1 Y. And then there's a 2S, but there's a, yeah, so it'll be minus 2S. There's a negative 1, but then you're adding 4 to it, so it'd be plus 3 is equal to this giant thing again. But I'm going to move this to the other side because all I want to do is solve for Y. So that means I'm going to just isolate the Y. So there's just going to be this is equal to all of this. But then it will be plus 2S minus 3. And this right here factors to S minus 1 squared. So it's like as if I'm just dividing everything. To get Y, it's like as if I'm dividing everything by S minus 1 squared, which is really nice because all of these are also S minus 1 here. So, you know, I made up this problem so that it'll be nice. So you'll have the 5, it'll be 5 factorial over S minus 1 to the 8th, because I'm just dividing by S minus 1 squared. So the 6 becomes to the 8th. And then plus 4 factorial S minus 1 to the 5, 6, 7 plus 3 factorial S minus 1, 4, 5, 6 plus 2 factorial over S minus 1, 3, 4, 5 plus 1 factorial over S minus 1 to the 4th plus, I guess we could say the 0 factorial over S minus 1 to the 3rd. And then the last one is just going to be S minus 3 divided by S minus 1 squared. Okay, this last one, okay, so we found, what did we do? We found our capital Y, right? We took the equation, we did the Laplace transform of every single term on this equation, and then it's just algebra. We're just trying to isolate capital Y. Of course, these greens here, I just applied these conditions. So that's nice about the Laplace transform is that unlike the method of undetermined coefficients where you apply the initial conditions at the end, with the Laplace transform, you apply those initial conditions immediately after you've transformed the equation. So these little y naughts and y primes, they all become numbers. So the only letters that are remaining here are capital Y and S. And then you're just solving for capital Y in terms of S, and we did that. This is it. So what do we do now? To get the solution, we have to do the inverse Laplace transform on this. So to do the inverse Laplace transform, actually all of these 1, 2, 3, 4, 5, 6 entries in the front here, they actually are really, really easy to take the inverse Laplace transforms of. But it's just this last piece that's a little bit more harder because they don't actually show up on the table. So we'll just do partial fractions on this. So this can be decomposed into A over S minus 1 plus B over S minus 1 squared. And if you were to solve for the A and B, which I'll write out, it's just really short, but it'll be 2 over S minus 1, and then it'll be plus 1 over S minus 1 squared. That's if you were to solve for the A and B. So now that you have that, what I'm going to do is I'm going to just take the inverse Laplace transform of this. But what I'm gonna use is this. So most all those earlier terms, you can actually just use this result. So I'll just say we have this, right? T of n is equal to this. So this first one, 5 factorial of s minus 1 to the 8th power, looks like if I were to invert this, it looks like this, but with n is equal to what? Good. N is equal to 7. Because you have a n plus 1 on the bottom, that's going to have to mean equal 8. So that means n has to equal 7. So if n is equal to 7, then it's going to be 7 factorial over s over 8. It looks like it's kind of like this, but with an additional e to the what multiplied to it. It's been shifted, right? Because it's s minus 1 on the bottom. So it looks like this looks like it's going to be like an e to the t multiplied with t to the 7th, right? That's what it looks like to get that. But the issue is that t to the 7th would give you t 7 factorial over s minus 8. Well, of course, if you do the e to the t, you'll get. So what is the Laplace transform of this? It would be 7 factorial over s minus 1 to the 8th, right? But you want 5 factorial. So you could just multiply by 5 factorial and divide by 7 factorial. So that's kind of the idea for these. So I'll go ahead and write all that. So we'll just say that this basically, it would be convenient if you can just say this is the same as 5 factorial over 7 factorial. And then it would just be like 7 factorial over s minus 1 to the 8th. This one is like n is equal to 6. So this will be 6 factorial. So I want the top to be 4 factorial, the bottom to be 6 factorial. So this is like the multiplication that I'm compensating. And then it's going to be 6 factorial over s minus 1 to the 7th. This one is like with n is equal to 5. So this would be 3 factorial over 5 factorial times 3 factorial over s minus 1 to the 6th. And this is the thing I'm compensating by. Oh, sorry. This is 5 factorial. And then this entry looks like n is equal to 4. And so this is the extra factor. This is like all of these terms are the exact same. So this 5 factorial over s minus 1 to the 8th will be equal to this because the 7 factorials will cancel each other. This next entry is like n is equal to 3. So it's going to be plus 1 factorial over 3 factorial times 3 factorial over s minus 1 to the 4. Plus this last one is like n is equal to 2. So it's going to be like 0 factorial over 2 factorial, 2 factorial over s minus 1. I'm going to just move to the next line here. So I'll just say plus 2 factorial s minus 1 to the 3. Again, these are just factors we're multiplying by. And then this last piece right here is just, we already did the partial fractions for it. It's s minus 1 plus 1 over s minus 1 squared. Now let's just compute the inverse Laplace transform. So y of t would mean just taking the inverse Laplace transform for all of these entries right here. So I'll just write it like this and say, we're just now going to take the inverse Laplace transform. So this 7 factorial over s minus 1, 8 factorial is just going to be Like literally, we just did this one. So it's this right here and this, right? So that means that it's going to be equal to E of t, E of t, e to the t, t to the seventh. 5 factorial over 7 factorial is like 1 over 6 times 7, and that's 1 over 42. And then you'll have dt 7t. Okay, the next one. This 6 factorial over s minus 1t, s minus 1 to the 7th. Okay, so 4 factorial over 6 factorial is like there's 4 factorial and 4 factorial on the top and the bottom that cancels. So there's only like 5 times 6 on the bottom. So that's just 1 over 30. But do you know what the inverse Laplace transform of 6 factorial over s minus 1 to the 7th is?
E to the t times t to the 6.
Yes. Okay, 3 factorial over 5 factorial is just 1 over 20. What's the inverse Laplace from 5 factorial? What's this? Yes. This is just going to have 3 times 4 on the bottom, so this is 1 over 12. What's the inverse Laplace transform of this? Good. And then this one is just going to be 1 over 6 after you've done that. And then the inverse Laplace transform of t3 factorial. Yeah. You see how like it's just a shift on all of these entries, right? So then you're going to do the last one is 0 factorial is just 1, and then 2 factorial is just 2, so it's going to be half times the last one is going to be e to the t squared. What's the inverse Laplace transform for 2 over s minus 1? Yes. And then what's the this one is like it's like this see here the I'll just write it here. So this is like s minus 1 squared, but it looks like this is going to be s squared here if n is equal to 1. But if n is equal to 1, it'd be n factorial over 1 factorial, which is 1, over s squared. So the n minus 1 case, n equals 1 case would be n 1 factorial of s squared. This looks like this, but it's been shifted. So what do you think the compute this? Oh, sorry, I made a mistake. This b right here is a -1, so it's going to be negative here. I did the partial fractions here, so this will just be negative. So minus 1 over s squared minus s1 s to the s minus 1 squared. Looking at this would be, so this is like t, the Laplace transform of t would have been 1 over s squared. So 1 over s minus 1 squared's inverse Laplace transform would be yeah, t to t. So this will be minus t to t. And that's it. So I mean, you can simplify this a little bit, like by just factoring out at e to the t. So you could just say this is like the same as, and I'll just reverse the order. So I'll just say, well, I'll just say the t, factor out a t squared, and then it'll be half plus 1/6 t to the 1, because I factor out a t squared, plus 1/12 t to the squared, plus 1 over 20 t to the third, plus 1 over 30 t to the fourth, plus 1 over 42 t to the fifth. and then e to the t, because they're all going to be multiplied by ut, plus 2 e to the t minus t e to the t. So why did I write it like this? Is because when we went back and check, this is like your a naught, this is like your a1, this is like your a2, this is like your a3, this is your a4, this is your a5. This is like your c1, and this is like c2 is equal to -1. If you were to use the method of undetermined coefficients, those would have been your a naught, a1, a2, a3, a4, a5. However, it would have taken you ages to do it if you did the method of undetermined coefficients because of the mess that you just saw before. But we were able to do it in about 2 pages using, so literally we did it in like 2 pages using Laplace transforms. So that's the power of using Laplace, because this would have been ridiculous. And most software, if you like use Mathematica or something, under the hood, they're not doing method of undetermined coefficients. They're using Laplace transforms. It's much more efficient. Like not just efficient human writing wise, but like computationally, it's more efficient to compute the solution to a Laplace transform using Laplace solution to a differential equation using Laplace transforms or something like this. And computer scientists would care about that. They'd want to find an algorithm that would solve this equation with the least amount of operations, right? So this would be more efficient, and you can see why, because as a human, it took us less work than if you were to actually compute the product derivative of this, the second derivative of this, and all that would have been insane. And then you have to come up with a linear system with 6 equations and solve for the a naught, a1s, and a2, a3. But this allows you to do it right away without having to do all that. So like on the final, you won't, this was more for your enrichment. Like I wouldn't ever ask you to probably do like this kind of, right, this insane looking. I mean, it's not that bad, but it's just kind of tedious to have to take, the Laplace transform of all these terms. And then there is a little bit of partial fractions, but it's a really easy partial fractions. All the other terms are just building off of this single entry on the table and doing Laplace transforms or inverse Laplace transforms with some kind of shift. It's not bad, but it's too long, I think. So on the test, you'll probably get something like the one that we just did right here. This first one, like this one right here, is like easier, I think. And you'll just get 1 on the final. And so the final will only see a couple of Laplace transform problems. But it's good to know because this is like something that's very classic to this course. So it's good that now you went through all this work of trying to compute the Laplace transform, compute the inverse Laplace transform. And now you finally see how it actually gets used to solve a differential equation. Basically, you're just doing Laplace transform of the equation, solve for capital Y, and then inverse Laplace transforming the solution. So that's it. Yeah, thanks for staying. I'll just post this for the other people. And yeah, have a good day.